Ronen Shaltiel. Will tell us about pseudorandomness. What is pseudorandomness?
What is pseudorandomness? Okay, so this is a joint work with... Some of this always happens to me, right? I'm like, so I know that I am speaking and I'm a regular joke, but give me some time to get warmed up. So this is joint work with Sergei Atmenpo, Valentin, and Russell. And in fact, this is the first talk in this conference about derandomization. So let me tell you a little bit about derandomization. So one of the most important open problems in randomized complexity theory is to derandomize probabilistic algorithms. We want to make them deterministic. Specifically, we want a transformation that takes as input a polynomial time randomized algorithm. This is an algorithm that in addition to the input also tosses coins. And we want to cure it of its unhealthy addiction to random bits and make it into a polynomial time deterministic algorithm. Okay, so that's the goal for this talk. It's a very well-known and important open problem, and unfortunately, by works of Cabanets and Impagliazzo, we know that it's very hard to achieve this goal. If we can do this thing, then there will be circuit lower bounds, and these circuit lower bounds are currently not in our reach. This has been the case for 35 years now, so right, I mean, don't get your hopes up. But we strongly believe in these lower bounds. Therefore, what we do is what's called the hardness versus randomness paradigm. Namely, we restrict our attention to proving the converse of this. That is, we want to show that if we have circuit lower bounds, then we can perform this task. Okay? So that's the goal in this area. This is called hardness versus randomness. And I just... Oops.
Don't press the button.
What would happen if I press it again? I mean, I wonder. So, since this is a workshop on extractors, right, I want to mention that there is a formal sense following Trevisan's work, but even though these are conditional results, right, I mean, if horses can whistle, then pigs can fly, and a lot of people, and you know who you are, right, I mean, some of these people, a lot of people don't like conditional results. These are really explicit construction problems. So all of these hardness versus randomness trade-offs hide inside them a combinatorial ingredient, right? Typically a seeded extractor or a seeded disperser, and the key is to construct seeded extractors or seeded dispersers with additional properties that enable this to go through. Okay? So let me give you an important example of a hardness versus randomness trade-off. This is a celebrated theorem of Impagliazzo and Wigderson from 1997. It has this form: under plausible hardness assumptions, randomized algorithms can be efficiently derandomized, and the lower bound is the following, right? And if you don't like these things, right, and I'm just reading this, don't pay attention, that there is a problem in d time 2 to the O of n that requires very large circuits which are exponential, and the conclusion is that BPP equals P, meaning that every randomized algorithm that runs in time t can be simulated deterministically. We can get a deterministic algorithm that runs in time polynomial in t, and this is great. We all love this theorem. It's wonderful. But sometimes a polynomial slowdown is a deal breaker and it's not good enough. One example for such a setting is the case of algorithms solving K-SAT. So the best K-SAT solvers in the literature run in time which is exponential, 2 to alpha times n, when alpha is some constant, and this constant is typically close to 1. And the best known algorithm for k greater than 3 is by Pature, Pudlak, Zaks, and Zain. It is randomized. And now the question that I want to keep as a motivation is, can we derandomize this algorithm using hardness versus randomness? And the thing is that polynomial slowdown is not good enough, because polynomial in 2 to the alpha times n will be larger than 2 to the n, and we don't need this fancy machinery to come up with an algorithm that runs in time 2 to the n for solving K-SAT. What we would like is what I'll call negligible slowdown. Namely, we want to take the running time of the algorithm and multiplying by something which is smaller than exponential, so that we will preserve the running time. And this is indeed what we do in this work, and we show that the PPSZ algorithm can be efficiently derandomized in this form under plausible hardness assumptions, and this is the first application of hardness versus randomness for NP-complete problems. Now note, but I didn't say every randomized K-SAT solver. I said the PPSZ algorithm, and this is because I'm going to build on very specific properties of this algorithm. And for this, I need the definition of an OPAP algorithm, one-sided probabilistic, almost polynomial time algorithm. So this is just some instantiation of parameters for a one-sided error randomized algorithm. So what is an OPAP algorithm? This is a randomized algorithm that runs in time t of n, which is less than exponential. Okay? And let's think about algorithms for a SAT. If a formula is satisfiable, then the probability that the algorithm will find a satisfying assignment is larger than epsilon. And think of epsilon as very, very small, so that 1 over epsilon is larger than t. And of course, if the formula is not satisfiable, the algorithm cannot come up with a satisfying assignment. And the observation of Paturi and Pudlak is that many K-SAT solvers in the literature, including the PPSZ algorithms, are based on OPAP algorithms. And specifically, PPAP is based on an algorithm with epsilon, which is 2 to the minus alpha times n. And the way you get the results that are reported in the abstracts of these papers is that you repeat this OPAP algorithms 1 over epsilon times in order to make it a constant error algorithm, like the way we like them. And this gives you time 1 over epsilon, which is 2 to the alpha n. This is the time that is reported in the abstract. This is why we end up with these times. And what we really do in this work is that we de-randomize OPAP algorithms. We give a method, a hardness versus randomness trade-off for OPAP algorithm with negligible slowdown. So let me tell you what the theorem is. So here is the Impagliazzo-Wigderson theorem. Now we're no longer interested in algorithms with constant success probability. We want algorithms that are one-sided error and have very small success probability. If we were to instantiate the Impagliazzo and Wigderson theorem in this case, the time that we would get is polynomial in t over epsilon. And the whole point is that in this new work that we have, instead of polynomial in t over epsilon, we get polynomial in t, but linear in 1 over epsilon. That's the whole point, right? Because 1 over epsilon is the larger quantity here, and this is what we want to save in. And unfortunately, we have to assume a stronger assumption. Rather than assuming a lower bound against standard circuits, we will be assuming a lower bound against non-deterministic circuits. Now, if there are math people in the audience, whenever I say circuits in this talk, feel free to think about algorithms. When I say size, feel free to think about time. It's not the same thing, but for the purpose of understanding this talk, it's good enough. Okay, so what are non-deterministic circuits? These are exactly what you expect, right? I mean, these are circuits which make non-deterministic guesses that have non-deterministic power. And this assumption is a standard assumption in this pseudo-randomness literature. It comes up in a lot of other settings. And as I'll show in a couple of slides, it is in some sense necessary. Okay? And of course, right, I mean, this is exactly what you need for the application that I mentioned. So if you have such a trade-off, since you pay linearly in 1 over epsilon, which is the main quantity here, right, then polynomial in 2 to the little o of n is still 2 to the little o of n, and 1 over epsilon is 2 to the alpha times n. So you get a derandomization running with the time that is matching the time of the randomized algorithm, and this is best possible in the sense that even to amplify the success probability from epsilon to a constant requires multiplying the time by 1 over epsilon, and we essentially do this. Okay, so you can't hope to do better than that.
Ronen, sorry, I mean, I'm missing something super basic. If I have can't I solve every problem in NP in non-deterministic time n?
No, I'm not saying that the algorithm runs in non-deterministic time.
The assumption.
No, the assumption.
I'm just confused. Can't I just guess and not deterministic?
No, but the assumption is that the assumption is that there exists a problem in E, which is hard for non-deterministic circuit. This right? I mean, this is a plausible assumption.
Like set, for example, or
What?
something. So this problem, for example, cannot be set.
No, it can't be set, right? But right, I mean, but E has complete problems, and we like, for example, just like we believe that X is different from NP, right? This is roughly the same thing, but you have a non-uniform model here.
Even complement of sub.
Okay. Right, you're right, and a co-NP problem might satisfy this, right? So this is a very plausible hardness assumption. Okay, so all this thing.
So it's like you're looking for a epsilon heating set generator where the seed length is log t plus 1 times log 1 over epsilon.
Very good. So this is the purpose of this slide, right? And so all this story about K-SAT, right, is just an excuse to study pseudo-random generators and heating set generators, which are now defined with very low error. Right, so that's really what this talk is about. So if you don't care about K-SAT, forget about K-SAT. And let me give you a crash course in derandomization. Okay, so the key notion in derandomization is what's called a pseudo-random generator. What is a pseudo-random generator? So let's see some circuit, and we want to fool this circuit. A pseudo-random generator is a function g that maps few bits, r bits, called the seed, into many bits, n bits, and it has the property, it is an epsilon PRG for C if C does not distinguish between a uniform input and a pseudo-random input, a uniform output of a pseudo-random generator. So you can see that with the two experiments that I have here I have the experiment where C is given, UN stands for the uniform distribution on n bits. Here I'm giving C the uniform distribution on n bits. Here I'm giving C the distribution which is obtained by sampling a random seed of length r, applying the pseudo-random generator to get what I call a pseudo-random string. And then I feed that into C. And what is written here is that these two experiments are roughly the same up to epsilon. Right? So that's a very important notion. If you only take this from the talk, right, then that's enough. Okay. Now, I'll also be interested in a weaker variant of a pseudo-random generator called the heating set generator. What is a heating set generator? A heating set generator is a relaxation of a pseudo-random generator in which I only require that if this quantity is larger than epsilon, then this is larger than 0, right? Or stated this way, if the circuit accepts an epsilon fraction of the inputs over the uniform distribution, then it must accept at least one pseudo-random string, okay? So that's a heating set generator. Why do we care about these things? Because this definition of pseudo-random generators and heating set generators are exactly what you need if you want this application of derandomization of randomized time algorithms. So how does it work? If I have a pseudo-random generator or heating set generators for small circuits, I have a deterministic simulation of randomized algorithms that works as follows. Give me your randomized algorithm and your input, okay? I'm going to go over all 2 to VR inputs, over all 2 to VR seeds to the pseudo-random generator. For each one of them, I'm going to apply the pseudo-random generator. For each pseudo-random string that I obtain, I'll instantiate the randomized algorithm with the input using this specific pseudo-random string, and I will collect 2 to VR answers given by the algorithm. And then, depending on whether the algorithm is one-sided or two-sided, I need to decide what I will do. In the case that we've just seen, when the algorithm has one-sided error, an OPAP algorithm, if it is the case that even once I saw that the algorithm thinks that the formula is satisfiable, then I'm sure that the formula is satisfiable. In the case of two-sided error, I collect 2 to VR answers, and I answer according to majority vote. If more than half of the answers think that the input is in the language, then I answer yes, and otherwise I answer no. So the total running time of this, and it's completely trivial to see that the definition of heating set generators and pseudo-random generators immediately give that this simulation works. And as you can see, the slowdown of this approach is 2 to the r times the time of g, right? I mean, this is the initial time of the algorithm, and the deterministic time is multiplying by this quantity, okay?
Why did you choose n square circuits? That's just an
N is good enough. There's this issue of how you transform Turing machine into, it doesn't matter, right? Okay, so now, as I hinted, the quantity epsilon that comes up here is exactly the same epsilon that came up in the previous slide, the success probability of the OPAP algorithm. And in order to handle algorithms with small success probability, where epsilon, which is very small, I need pseudorandom generators and heating set generators which work for very small epsilon. And let's see what do I want for them. So first of all, for the result that I stated, I want a very short seed. It can be shown that the seed has to depend on epsilon. It has to be at least 1 times log 1 over epsilon. And it better be 1 times log 1 over epsilon, because 2 to the, if it would be larger, then 2 to the r will be larger than 1 over epsilon. Okay? So I want r to be 1 times log 1 over epsilon. And then, since I've already paid all that I'm willing to pay as a function of epsilon, it better be the case that the time of g is polynomial in n. And this is very different than the standard Nissan-Wigderson setting, in which we typically allow the time of g to be polynomial in 2 to the r, because we don't care about polynomial slowdown, right? I mean, once we pay 2 to the r, we might as well pay 2 to the 10r. So this is somewhat different than the way these parameters are usually set up. Okay? And now the question which I'm interested in, so everything until now was an excuse. What I am interested in is that can we construct such pseudorandom generators and heating set generators? And when we can, under what assumptions? What kind of lower bounds do we need? Okay? So I'll give you a survey on low error pseudorandom generator. So here is a table. The way this table works is that every row is going to be an object. The first object that I'm going to consider a pseudorandom generator with large error. So whenever I write quarter, I mean large, right? So a quarter is large, or 1 over n. And whenever I write epsilon, I mean small. So epsilon is smaller than 1 over a polynomial, okay? And the columns over here are going to be hardness assumptions, right? So we've already seen that I'm sometimes assuming hardness assumptions against deterministic circuits, and sometimes I'm assuming hardness assumptions against non-deterministic circuits, and I'm going to assume hardness assumptions against even stronger circuits in a moment, okay? So the first row is the classical result which I just told you of Impagliazzo and Wigderson. If you're interested in a pseudorandom generator for the higher regime, then everything is dandy. There are pseudorandom generators with seed with r order of log n. They run in polynomial time, and it's great. Okay? The next thing that I will consider is the case of heating set generators for small epsilon, when epsilon is small. And this is the result that I just told you about, the derandomization of OPAP algorithms. This is a heating set generator with seed length order of log n plus 1 times log 1 over epsilon. And this is good enough for the application, but I'm assuming hardness against non-deterministic circuits. Do I need to assume hardness against non-deterministic circuits? Well, in some sense, I do. The first thing is that we have results. This is with Viola, and this is with my student Artmenko, showing that if your construction works in a certain black box manner, and all constructions in this literature work in this black box manner, then you cannot get a hardness versus randomness trade-off that starts from a hardness against deterministic circuits. Okay? And furthermore, what we have in the paper is we also show that an epsilon heating set generator for small epsilon imply hardness for a circuit model which is an intermediate model between deterministic circuits and non-deterministic circuits. What is this model? The circuit model is non-deterministic circuits, but where the number of non-deterministic guesses is small. is sublinear. It approaches, it's slightly less than the length of the input. So that's not the way we typically think about non-deterministic computation, but it at least shows that there's a good reason why we can't get that, right? I mean, this object implies an assumption that seems much stronger than this one. Okay? It's open to construct, or whether it is possible to construct heating set generators under this intermediate assumption. Okay, let's talk about the next line. So now I'm interested in epsilon pseudo-random generators rather than heating set generator. And here something happens which we find very surprising. Okay? Usually, heating set generators and pseudo-random generators are roughly the same thing. And in fact, for the higher regime, right, we can trade one for the other. If you give me a heating set generator, I can convert it into a pseudo-random generator. But here, what happens is that for epsilon pseudo-random generator, we can show that it is impossible to construct them under hardness assumption for non-deterministic circuits, like we were able to construct heating set generator, and it is even impossible to construct them under hardness assumptions against pH circuits. So what are pH circuits? So just like I had standard circuits, deterministic circuits, and then non-deterministic circuits, non-deterministic NP is the first level of a polynomial time hierarchy. Now I'm thinking about circuits which can, for free, compute functions in the polynomial time hierarchy in pH. So these are pH circuits. This you can think about it as extensions of non-deterministic, right? When I count the number of alternations. Okay? And these kind of circuits appear in this literature. Okay? So it turns out that there's a big difference. You cannot construct epsilon pseudo-random generators even if you assume an incredibly strong hardness assumption. Right?
So by impossible, you mean even if the seed is log n plus 10 log 1 over epsilon?
Yeah, the key thing is that if you want your pseudo-random generators, essentially what happens is that epsilon cannot be smaller than 1 over the running time of your pseudo-random generator. This is essentially what happens. Right? So once you get in trouble if you have a black box construction that is doing that. Okay? And essentially what we show is that if you had such a construction, then I can use the proof of that construction to compute majority by a constant depth circuit that is too good. And this is where pH comes in. So what happens is it's like an FSS type argument. I take the reduction, I think about it as a function of a big truth table, and then it becomes a constant depth circuit, and I play with it, and I see that if you're doing too well, you're solving, right? I mean, I could use you to compute majority.
So leave and die the worst case to average case reduction where epsilon, oh yeah.
This is going to come up?
So is it conceivable you could get an epsilon squared instead of epsilon?
No, nothing is possible. Nothing is possible, right? And in fact, I'll come back to this, right? I mean, in retrospect, this explains why you weren't able to do hardness amplification, because this result also holds for hardness amplification. Okay, right? I mean, you were able to do hardness amplification into a function which is non-Boolean, but you couldn't do the final Goldreich-Levin-like step, right? And the reason you couldn't do it is because it's impossible. Okay, so I'll come back to this. Okay, and so now, right, I mean, so once we see that, when we try to get around it, so what do we do? Well, if you look, we looked at this lower bound, and what we really show in this lower bound is that we show a lower bound against something I'll call a half versus half plus epsilon pseudo-random generator. So what is a half versus half plus epsilon pseudo-random generator? When an alpha 1 versus alpha 2 pseudo-random generator is a version of pseudo-random generator with this weaker guarantee. The guarantee is that if a probability that the circuit accepts on a uniform input is smaller than alpha 1, then on a pseudo-random input, it cannot accept with probability larger than alpha 2. Now, this kind of rationale already came up in Amnon's talk a couple of days ago. This is the computational analog of what Amnon was interested in, right? So I'm not necessarily interested in controlling tests of all sizes, right? But I'm only interested in controlling tests of fixed sizes, alpha 1, and I only want them not to explode. Okay? And actually in the paper, we have exactly this multiplicative, the way we define it is exactly this multiplicative way in which you want it in your talk. So maybe, right, I mean, this will make you like this better. Okay, so, right, but maybe I've said, right, let me just, maybe this is too fast. So just let's think about it. So now with this new notion, an epsilon pseudorandom generator is an alpha versus alpha plus epsilon pseudorandom generator for every alpha, right? I mean, no matter what is this quantity is no more than alpha 1 plus epsilon, right? And we know that we can't do it when alpha is large, when alpha is a constant. Oops. So maybe we can do it when alpha is small, right? And we can. And what we do is we give epsilon versus 2 epsilon derandomization and pseudorandom generators under hardness assumption. Sometimes we get the correct hardness assumption by non-deterministic circuits. Sometimes here we need to assume hardness for sigma-free circuits because we lose something in the reduction. It's not that important. I'll only mention that the seed length that we get here is also not optimal, right? I mean, this square shouldn't have been here. This is an artifact of a Nissan-Wigderson generator. The Nissan-Wigderson generator has this well-known limitation where in some settings the seed is square of what it should be, and this is why we get that, okay? And I'll also say that in the paper and also in the previous papers there's something called a pseudorandom generator for non-Boolean distinguishers, which I'm not going to talk about, but if you like pseudorandom generators and you've never heard about pseudorandom generators for non-Boolean distinguishers, come talk to me. Okay? You like them, there are a lot of here we know very few things. Okay, how much time do I have?
10 minutes.
10 minutes?
No, wait, no.
30 minutes.
20 minutes. Start for 20 minutes. Fine.
Okay, so I want to show you, right, I mean, some of the high-level idea of the constructions. And let me start with showing you the construction of the epsilon heating set generator with seed length order of log n plus 1 times log 1 over epsilon. And the construction is extremely simple, right? I mean, I'll be able to do it in a single slide, okay? So here is how it works. Remember, I'm going to assume a hardness assumption against non-deterministic circuits, okay? Now, by what I'll now call classical hardness versus randomness, right? I mean, things that were done 15 years ago, right? We by now completely understand the high error case. So if you give me a hardness assumption against non-deterministic circuits, I can give you a high error heating set generator for non-deterministic circuits, not for standard circuits, but for non-deterministic circuits. This heating set generator is stretching order of log n bits to 2n bits, and it's computable in a time polynomial in n, right? I mean, that's what you get from this sequence of works. And now, here is my final construction. I'm going to construct a heating set generator G prime, and the second ingredient which I'll use is a family of pairwise independent hash functions that we all know. The way I set things up, these hash functions are going to be from log 1 over epsilon bits to n bits. So this is not the standard way you set things up because log 1 over epsilon is smaller than n. Right? So this is, the word hash is not in place, but never mind, I can do that. Okay? And such families of pairwise independent hash functions can be sampled using 2n random bits, right? And this is why we have 2n over here. What is the construction? So the seed of my new heating set generator is going to be composed from two parts. One is a seed, S1 is a seed for this generator. I'm going to take this seed, okay? Apply this heating set generator, so I'm going to get a 2n bits string, and then I'm going to use this 2n bit string to select a hash function. So rather than selecting a uniform hash function from the family, I'm selecting the hash function in a pseudo-random way. And then once I have this hash function, I apply it on my second seed, which is of length log 1 over epsilon, to get n bits. So as you can see, the seed length is indeed order of log n plus log 1 over epsilon. 1 times log 1 over epsilon. And the proof is very, very simple. The proof is a non-deterministic reduction. So let's assume that G prime is not an epsilon heating set generator, okay? Then what does this mean? This means that there exists a small circuit, deterministic circuit, which accepts an epsilon fraction of the input, and yet it doesn't accept any pseudorandom string, any output of a heating set generator, okay? Let's consider the following procedure. The procedure D, which gets as input a name of a hash function. Think of Z as 2n bits, a name of a hash function. And what it checks is whether there exists a second seed such that if I were to apply the hash function with this Z on the second seed, then C will accept. And as you can see, right, I mean, by design, this is a small non-deterministic circuit, right? I mean, this quantifier is non-determinism. And we indeed have, but for every S1, D doesn't accept G of S1 because it didn't accept any pseudorandom string. And the pairwise independent property immediately gives that if I were to apply D on a uniform Z, if I were selecting the hash function at random and not in a pseudo-random way, then because of the heating or sampling property of pairwise independent hash function, since the set of inputs accepted by C is of weight at least epsilon, right, then one of the outputs of H, which is, right, I mean, there are 1 over epsilon outputs, one of the outputs is going to hit this set of accepting inputs with large probability, with constant probability. So this means that D will accept a uniform input with large constant probability. And this means that this circuit D, this small non-deterministic circuit D, distinguishes the output of this heating set generator, G, from uniform. And that's impossible because we were assuming that this is a heating set generator. Okay?
So you could have used an input disperser there instead of the was.
Yeah, the critical thing about the disperser is the correct dependence on epsilon, right? I mean, so what I need is a heater, right? I mean, the dependence on delta is not important, but the dependence on epsilon is crucial. I need this 1 times log 1 over epsilon thing. Okay? Okay, so now let me give you an intuition. Why are epsilon pseudorandom generators harder than epsilon heating set generators? What is happening here? And indeed, what we try to do in this line of work is we try to match this intuition that we have. And the intuition is that the possibility or impossibility of pseudorandom generators, if we assume hardness against type X circuits, really depend on the complexity of the following promise problem. So what is this promise problem? I'll call it the alpha 1 versus alpha 2 promise problem. And this problem is the following problem. You're giving as input a function D from n bits to 1, but you're giving it as an oracle, right? So the game is that you are allowed to send inputs to it, and it replies an answer, okay? And then your goal is to determine whether D accepts less than alpha 1 inputs or more than alpha 2 inputs, and you're promised that one of the two things happen. That's the game. Right? That's a promise problem. So let's view this for a moment, right? So for the case of alpha versus alpha plus 1 over n, this is just sampling, right? I mean, you sample, and you decide in polynomial time by randomized probabilistic algorithm. This is in BPP, and BPP is in P/poly. And this is essentially why in Pagliazzo and Wigderson, for the alpha versus alpha plus 1 over n game, this is why we should expect that you can do it with hardness against deterministic circuits. For the case of 0 versus epsilon, that's like 0 versus epsilon is like a heating set generator, okay? Because it's, right, this is the difference between 0 accepting inputs or epsilon accepting inputs. This is possible in NP by simply guessing, and this is why we expect that this should be possible by a non-deterministic reduction, by hardness against non-deterministic circuits. For the case of half versus half plus epsilon, right, this is impossible even in the polynomial time hierarchy. And this is the source of a lower bound why we can't do half versus half plus epsilon even by pH reductions. And the interesting, the only non-trivial line here is that the case of epsilon versus 2 epsilon is what is known as approximate counting of NP witnesses. This is exactly what you need. An approximate counting of NP witnesses is solvable in BPP to the NP, that's in the polynomial time. A hierarchy by the classical result of Stockmeyer and Jerome Valiant and Vazirani, right? So this is why epsilon versus 2 epsilon is very different than half versus half plus epsilon. And indeed, the game that we play in these constructions and lower bounds is we try to match this table, right? When we prove lower bounds, we try to reduce to these bounds, okay? And when we prove upper bounds, we try to use the things that come up here inside our efficient algorithms that implement the proof. Okay?
But half versus half perception you can do in p-space.
In p-space you can do, or even maybe even in like some level of a counting hierarchy below p-space. Yeah.
So
and that's good
some
enough.
Assumption like if x doesn't have
Yeah.
sub-x
Yeah, that's good enough. Yeah.
the matching programs.
Yeah. And that's true. Right, so it's easy to show. So if there was another column here, like p-space circuits, or I don't know, p to the pp to the pp to the pp to the pp, maybe 4 times, then that's good enough. Okay. So how much time do I have?
7 minutes, 32 seconds.
33 seconds at least. So the last thing I want to show you is the construction of epsilon versus 2 epsilon pseudorandom generator. I'm going to give you the high level, right? This is far more complicated. I'm going to give you the high level idea. So we start with a hardness assumption, and we want to get a pseudorandom generator with large stretch. And what we do is we follow the approach of Nissan and Wigderson. We first construct a pseudorandom generator, an epsilon versus 2 epsilon pseudorandom generator with 1-bit stretch. And then from this, it turns out that we can use the Nissan-Wigderson generator to get a pseudorandom generator with large stretch. There are details to take care of, but if you're familiar with the Nissan-Wigderson generator, right, I mean, you can do it, okay? So now I want to show you this part, and let me try and actually show the construction. And the construction is inspired by that paper that Luca mentioned of Trevisan and Vadan on extracting randomness from sampleable distributions. So here is the construction. It's the similar structure to what I just showed. We start with a hardness assumption for pH circuits, whatever these are. No, I don't care. And then it turns out, usually the first thing that you do in constructions of pseudorandom generators is hardness amplification. And there is a very nice hardness amplification result by Trevisan and Vadan showing that under this assumption, you can get a function that is computable in polynomial time from n bits to omega of n bits, which is extremely hard on average for small circuits, right? Namely, on a random input, a pH circuit can compute it with probability not much larger than 2 to the minus n, 2 to the minus n prime over 3, okay? Now, typically, this is the whole game. Once we get there, right, we can take this function, which is not Boolean, okay, and we concatenate it with an inner code, or if you're a cryptographer, you say we do Goldreich-Levin, and then we'll get a Boolean function with roughly the same hardness. But we know that this is impossible. Our lower bounds show that this cannot be done by a pH reduction, okay? Still, we're going to try to imitate this approach while never saying the word hard function, right? I mean, bypassing the difficulty, okay? So what will be the construction? So I'll construct a new function, g. It will have 2 inputs, x and y, and g of x and y is applying a seeded extractor. So there you can see there are seeded extractors inside these things. Applying a seeded extractor, a strong seeded extractor with 1-bit output on f of x and y. So I take the x, apply f, this hard function, and I extract 1 bit from it, right? That's kind of like hardness amplification. And syntactically, it's exactly like hardness amplification because a strong seeded extractor with 1-bit output is really a least decodable code, right? I mean, so it's just easier to say it in this framework. Okay, so I get this function, and now my generator, which stretches by 1 bit, is saying, on input x and y, output x and y, right? And this new bit, g of x and y. So that's a standard thing to do. And now I want to show that this construction is an epsilon versus 2 epsilon pseudorandom generator. So let's say that it's not an epsilon versus 2 epsilon pseudorandom generator. Then what does this mean? It means that there exists a small circuit C which on uniform input, when x and y are uniform and this last bit is also uniform, okay, outputs 1 with probability smaller than epsilon. And yet on a pseudorandom output, when x and y are uniform and the last bit is chosen by this function, okay, outputs 1 with probability larger than 2 epsilon. There is this gap, okay? So what is my proof strategy? My proof strategy is going to be, I'm going to try and contradict the hardness of this f. I'm going to try and show that I can construct a small pH circuit which, given x, is able to compute f of x with some noticeable advantage, okay? So how am I going to do it? The first step in all these like Goldreich-Levin type arguments is that usually I don't like the way things are stated here. I want to first fix x. So I want to show that for a noticeable fraction of x's, this gap is preserved even when I fix x. This is not true in this case, right? But something along the same lines is true, and we have to work with this extension. So let's pretend that it is true, but I can actually do that just for explaining the argument. Okay? So first thing I do is that I show that for a large fraction, for a noticeable fraction of x's, these two probabilities stay the same even when I fix x. Okay? And now, just like I did in the previous proof, I'm going to consider an intermediate computation. What is this intermediate computation? I'm going to consider the procedure t for a fixed x when it gets an input z, and you should think about it that t of x is trying to check whether z is f of x or not. It should output 1 if z is f of x and 0 if it's not f of x. Okay? But the way I'm going to describe, I'm writing it exactly how it works. Functionally, what it does is it answers 1 if this is less than epsilon, this probability is less than epsilon, this is exactly this, and it output and also that this probability is larger than 2 epsilon, where I don't know what f of x is, so I replace it with my candidate. I replace it with z. Okay? So it answers 1 if these two conditions are met. What is this computation? This is the whole point of the epsilon versus 2 epsilon regime. This computation, Tx, can be done by a pH circuit by this approximate counting thing that I just told you about it. Right? And this is where it's crucial that we use epsilon versus 2 epsilon and not half versus half plus epsilon, where we can't do it. Right? Now it's in the hierarchy. And now what does this help us? Well, for a good x, if x is one of these good x's, right, then f of x satisfies these two properties. This means that Tx will accept f of x. Now it may accept other strings, which are not f of x. I'm not claiming that it will reject all other strings, but what I am claiming is that the extractor property, right, is good enough to imply that the total number of inputs that Tx accepts is small. So Tx, in some sense, identifies whether z is f of x or not in a weak sense. Why is that? This is because if there were many z's for which Tx would accept, then look at this, right? The uniform distribution over these many z's would be a high mean entropy source, and these two conditions together will be saying that the seeded extractor, right, didn't work well. Right? So the property of a seeded extractor can be used to argue that there are only few z's which are accepted. Okay? So now, remember, what is my goal? Given x, I want to compute f of x. So given x, what I'll do is I'll sample a random accepting input of Tx, and this is something that a pH circuit can do. That's called uniform sampling of MP witnesses, and this is possible by the classical result of Jerome Valentin Vazirani and Bellaria Goldreich and Petrank. So overall, this computation was able to compute f of x. Now it makes errors, right? I mean, it only succeeds on few x's, and even for these few good x's, right, it only succeeds with small probability. But even succeeding with very, very small probability is already a contradiction to this hardness, right? And this is why it works. Okay, so I don't have time to talk about NB PRGs. So let me conclude. So what did I talk about? So I talked about conditional derandomization, hitting set generator, pseudorandom generators in the low error regime. If you're new to pseudorandomness, right, I mean, what I want you to take from this talk is the concept of pseudorandom generators and the understanding that using pseudorandom generators you can derandomize randomized algorithms, and that lower bounds are in some sense connected with pseudorandom generators in the way we currently understand things. So these are the, right, I mean, if you didn't follow a lot of this talk, right, I mean, it's great if you go home with this. Really what this study is about is it's about the power and limitations of pH reductions. So, right, if I connect to what I started with, really these are seeded extractors with kind of local decoding algorithms that are implemented by pH circuits. This is really what this is about. Okay? So it's really an explicit construction problem. Open problems, well, it would be very nice if we could come up with other way to derandomize SAT solvers. There are some applications of epsilon versus 2 epsilon PRGs and NB PRGs in the paper, but I think there should be many more. And for me, maybe that's not a very important thing. I would like to optimize, to completely fill up this table, that is to get the correct pseudorandom generators with the correct seeds under the correct assumptions. Thanks.